6.3 is about a special kind of function called an exponential function. So let me give you a definition. An exponential function is a function of the form f of x equals c times a to the x, where c and a are some numbers. C could be any real number, but a has to be a positive number in order to raise it to all kinds of powers. Like if you wanted to raise a to the 1/2 when x is 1/2, a would have to be a positive number because you can't take the square roots of numbers other than positive ones. Let's look at an example here. How about we plot f of x equals 2 to the x. So let's see, when x is 0, that's the easiest one, 2 to the 0 is 1. When x is 1, 2 to the 1 is 2. When x is 2, 2 to the 2 is 4. When x is 3, 2 to the 3 is 8. Now let's think, when x is -1, 2 to the -1 means 1 over 2 to the positive 1, that's a half. And when x is -2, 2 to the -2 is 1 over 2 squared, that's a quarter. And 1 over 2 cubed is an 8. So I plotted that and it looked like this. You can see the points here. There's 0, 1, there's 1, 2, there's 2, 4, there's 3, 8. Right here is 4, 16, something we didn't plot on our list, but I mean when x is 4, y is 16 on this curve. And these values of y show up here as well. There's -1, 1/2, there's -2, 1/4, there's -3, 1/8. And I just took those points that we calculated here and connected them with a smooth blue curve, and that's what it looked like. So you can see that when x is a large negative number, like over here or farther to the left, the corresponding values are really tiny, so the curve starts to hug the x-axis there. We say that this curve has the x-axis as a horizontal asymptote as we stick in these kind of large negative x's. Well, I thought we could try it again for another function. How about 3 to the x? So I'll calculate 3 to the x here for various x values. 3 to the 0 is 1, 3 to the 1 is 3, 3 squared is 9, 3 cubed is 27, and 3 to the -1 is a third, 3 to the -2 is a ninth, 1 over 27 again. I plotted those points, and that's what I got. So the green curve looks a lot like the blue curve. They both go through the point 0, 1, but then at x equals 1, the green curve is higher than the blue curve. And in fact, everywhere when x is positive, the green curve is higher than the blue curve. And that's because 3 is bigger than 2. If you can just make it out here, when the x's are negative, the blue curve is above the green curve. For instance, at x equals -1, 1/2 is bigger than 1/3. -2, 1/4 is bigger than 1/9. So the blue curve is above the green curve when x's are negative. But the green curve, like the blue curve, has this horizontal asymptote when x is a large negative number. How about this one? How about both of these had c equals 1. I thought we could try, c will be 3, and we'll plot 3 times about 1/2 to the x. So I'll plot 3 times 1/2 to the x. Let's see. When x is 0, y isn't 1 anymore. 1/2 to the 0 is 1, but times 3 makes 3. And then when x is 1, this is 3 times 1/2, that's 3/2. When x is 2, it's 3 times 1/2 squared. 1/2 squared is a quarter, so that's 3/4. And then 3/8. At x equals -1, okay, 1/2 to the -1 is the reciprocal of 1/2, that's 2. So this is 3 times 2 is 6. At -2, this is 1/2 to the -2, that's 2 to the +2. That's 3 times 4 is 12. And 1/2 to the -3 is 2 to the +3. That's 8, so 3 times 8 is 24. I plotted that, and it looked like this. So now, the red curve, some of these points didn't fit on the graph. Like I don't think I could fit this point, x equals -3, y equals 24 on this paper because it stopped at 20. But there you see negative 2, 12, and negative 1, 6, and 0, 3. And then, because this a here is less than 1, what happens as I move this way is that the red curve starts to hug the x-axis, but not for the negative x's, it does it for the positive x's. But otherwise, the red curve and the green curve and the blue curve all have kind of the same shape. It looks like the red curve is kind of a flip of one of the blue or green curves. And it's not exactly a match because one is not a copy of the other, but they're kind of comparable. I mean, they kind of have the same shape. One thing you can see here from this data is that when I increased x by 1 in the blue column, f of x increased by a factor of 2. That even happened here from 1/8 to 1/2, y doubles. I mean, you double 1/8 to get a quarter. You double 1/4 to get a half. You double a half to get 1. And obviously this is double, double, double. As x increases by 1, 2 to the x increases by a factor of 2. And 3 to the x increases by a factor of 3. Even from a 27th to a 9th, that's a multiplier of 3. 1/9 is 3 times a 27th. 1/9 times 3 is a third times 3 is 1, 1 times 3 is 3. And that's because, the x is just the exponent. So sure, if x increases by 1, this 3 to the x is 1 more 3 than you had before. It's 3 to the x times 3 to the 1. So these green numbers are increasing by a factor of 3 as I move this way, as x increases by 1. I mean, something different happens for the red curve, but not too much different. What's happening now is that instead of y increasing as x increases, y is decreasing, but it's still decreasing by a constant factor. As I increase x by 1, the y's are decreasing by a factor of 1/2. What we saw in those last examples gives us a good idea of what exponential curves look like in general. If you graph a to the x, and a is a number bigger than 1, you'll see a curve that's increasing. That is, y is increasing as you move to the right. And that's called exponential growth. But if a is a number less than 1, like a half, then you'll see a curve that decreases. That is, y is decreasing, and that's called exponential decay. Whether a is bigger than 1 or less than 1, you still have this horizontal asymptote. When a is bigger than 1, the horizontal asymptote occurs way over here where x is a large negative number. But when a is less than 1, then the horizontal asymptote, the x-axis, is an asymptote over here for the large positive x's. Another thing to notice about exponential functions is that a to the x can never be negative. Now, the c times a to the x could be negative if c was a negative number. But a to the x can never be negative, whether a is 2 or a half or 3 or 1/10. If you take a positive number and raise it to some exponent, you might get something large or you might get something small, but you'll never get 0 and you'll never get a negative number. So the graph of an exponential curve is always above the x-axis. It might get really close to the x-axis over here and here, but it never actually touches the x-axis. It's interesting to contrast exponential functions with linear functions. So in an exponential function, f of x has this form c times a to the x. The variable appears up in the exponent of some positive number. In a linear function, f of x is mx plus b, so the variable appears just being raised to the power 1 and then multiplied by some number m, which could be positive or negative. The m shows up in the graph of the function or in a table of values of the function, because remember, the slope of a line is the amount by which y increases or decreases when x increases by 1 unit. That is, if you took f of x plus 1 minus f of x, you'd get m. So m is the amount that y, or f of x, increases when you increase x by 1 unit. It's the fact that this is independent, this is a number independent of x, is because that's what gives lines their constant slope. Most curves don't have constant slope. Lines are the only ones that do. Well, the a shows up in an exponential curve this way. F of x plus 1 minus f of x doesn't equal a constant along a curve. Exponential curves don't have constant slope, but what they do have is this property that we saw when we looked down the table of values. If you take f of x plus 1 and divide it by f of x, you get this number a. So for instance, can you tell which of these functions is exponential and which one's linear? So the thing about linear functions is that when you move from one x to another, the amount that the quantity goes up or down should be a constant. So here, let's see, when I went from x equals 13 to x equals 14, both f and g went from 1.6 to 1.4. But then f is 0.1, and then it's 0.025 and 0.00625. G goes 6, that negative 0.8, negative 2. The thing to notice about g here is that when I move from here to here, I'm subtracting 1.2 each time. As x increases by 1, g of x goes down by exactly the same. Apparently this is a linear function with m equals negative 1.2. But in f, up here, when I went from 1.6 to 0.4, you could also view that as going down by 75%. This is 1/4 times that. So when I go from here to here, I'm multiplying by 1/4. And when I go from here to here, am I multiplying by 1/4? Sure, because 0.4 times 1/4 is 0.1. From here to here, that's multiplication by 1/4 again and again. So this is exponential with a equals 1/4. Something you might have noticed about the exponential curves we saw before is that they pass the horizontal line test. And here's a way you can think of the horizontal line test. The horizontal line test is testing to see if it's possible for two different inputs to have the same output, two different x's to generate the same y. And when a curve passes the horizontal line test, it means that it's impossible for two different x's to generate the same y. Two different inputs can't generate the same output. That's useful in solving equations. So let me look at an example here. Here's a new kind of equation. It's new in the sense that the variable that we're solving for is up inside the exponent. So the thing to notice is that both sides can be written as powers of base 3. I rewrite that 9 as 3 squared. Then the laws of exponents say I multiply these two exponents, so that's 3 to the 2 times 1 minus x on the right side. So here I've got two powers of 3 that are supposed to be equal. Because 3 to the x looks like this. It passes the horizontal line test. It's impossible for 3 to this number to equal 3 to that number unless these two numbers are equal. Right, so the exponent I see on the left has to equal the exponent I see on the right. And I rewrote that, I distributed that 2 through there, so that's 2 minus x. So now I turned this exponential equation into an equation in which the variable just appears, well, it's just a linear equation. I just got a little more room to solve it, so I added 2 to both sides. I beg your pardon, I added 2x to both sides to get 5x on the right. I subtracted 1 from both sides to get 1, so 5x equals 1, x is a fifth. Let's try that in another problem. How about 25 to the x equals 1 over the square root of 5 to the power 2x plus 1. So the trick again is to rewrite both sides so that they're powers with the same base. It looks like they're both powers of 5. The 25 is 5 squared. 1 over root 5. That's 1 over 5 to the 1/2. They're still not powers of 5 though. The thing to do is write 1 over a power of 5 using negative exponents. So 1 over 5 to the 1/2 is 5 to the negative 1/2. And they're not quite powers of 5 yet, but I can write them as powers of 5 if I use the laws of exponents to multiply these two and to multiply those two. So I'll get 5 to the 2x is 5 to the negative 1/2 times 2x plus 1. All right, 5 is 2x. Yeah. But see, 5 to the x is an exponential function. It passes the horizontal line test. It's impossible for this power of 5 to equal that power of 5 unless the exponents are the same. So it's not like an algebraic thing I'm doing to both sides to strike out the 5s. It's just that This implies that the exponents must have been the same. So now it's just a linear equation. I'll distribute the minus half through there, so minus x minus 1/2. Now I'm going to add x to both sides, so I'll get 3x is negative 1/2, and divide both sides by 3. And we're done.